Okay, welcome back, everybody. So today I want to talk a bit about hardware. Most of the class is going to be about software and autonomy and the higher level stack. But just to make sure we lay the groundwork and understand what we're going to be using, I thought I'd spend a day sort of talking a little bit about some of the details of the hardware. Now, someone asked last time, what's an EWA, which is like a reasonable question. I'm sorry I keep using EWA as a thing people know. I figured the best way would just be to bring one, so here you go. I also heard that it's hard to see from the back, so this will give you a sense of how frickin' heavy the EWA is. Okay, this is an EWA here. It's a beautiful piece of machinery. Okay, you'll notice it doesn't come with a hand by default. It's bring your own hand, and we'll talk about hands a little bit later. And I brought a bunch of hardware examples of some of the cool hands out there. This is what an EWA is. This is one of the many robot arms that you can buy, and you'll see in research labs these days, research groups working on manipulation. And there's a couple of reasons why this is a good choice, I think, for many research projects in manipulation. It's maybe a bit on the high-end, expensive version, but solid hardware that'll continue to work for you, even if you have a bug in your research code and slam it into a table or something like that. Okay, so we'll talk a little bit about what makes this EWA tick. And then towards the end, we'll talk more about all the dexterous hands. And I'll make sure that if I'll wheel this up to the back or something when we're done, and people can check them out. And you have to be a little careful with it. The bumps on the way over loosened a couple screws, and the fingers might fall off. But if you're gentle, then you can check them out. All right, so let's get you a robot. That's the goal for today. We'll talk mostly about robot arms. The hardware does matter. Right, your choice of what arm to sit next to and program or purchase, whatever, will matter. Your ability to do certain tasks will depend on the hardware capabilities. We're going to often use the EWA, but I'm trying to expand. I'd like to be at the point where sort of, I don't know, when I was young, we used to play these games like Mech Warrior, where you start off and there's like a robot, and you get to pick which bit you want here and you got the little display. I want the class to start off where there's like pick your robot, and you pick your robot, and then you go through and you make all the decisions and use that for the entire class. Most of my code uses EWA right now. It's not very baked in. If you just changed it for a Panda or something like this, almost all the demos would work, but you'd find a few corner cases where it doesn't work. Okay, so we'll talk about that, and I'll tell you why that's the arm of choice for now. Then we'll talk about how to simulate the EWA, just at the first level of detail. And I guess the biggest takeaway there is that the physics of the EWA is not enough to simulate the EWA, right? The fact that there's joints here and it's actually not falling down passively already sort of tells you that there's something else going on. And I didn't carry the control cabinet, but there's a whole control cabinet that comes with the EWA that you kind of have to simulate if you want to know what your commands are going to do between the place where you program your autonomy and send it to the robot. Just give me a second. And then when we get towards the end, we'll talk about, like I said, robot hands. There's a particular hand we'll use the most, but it's not exclusive, and I brought a bunch of different varieties. Yes?
Can you plug in the control?
Yeah. So you're going to see that in great detail. Yep. So not directly. We don't run their code in the middle of the simulation. We don't do the hardware in the loop version. You could. We haven't done that as a intermediate step. Okay. So again, when you see things in class, I almost always try to push the demos to deep note. So if you have been looking at the notes, you might have seen it already. Some of the demos I'll do today, you could just get them yourself if you're on the corresponding chapter. You click launch in deep note, and you should be able to run it just like your problem sets that you're starting on. Oh, I had a big note here to say, make sure you've signed up for Piazza. If you're an undergrad doing the CIM, make sure you've signed up for Canvas. And in particular, you should be signing up for the sections for the CIM. We need to lock that in so that people know which sections to go to on Friday if you're the undergrad in CIM. Yeah, and one thought, it was mentioned in the posts, but one thing that you should think about, I know it's impossible to ask you to pick your project groups now, but if you happen to kind of know who you're going to work with, or something, and that would be ideal if you were in the same section. We can maybe try to shuffle things around a little bit later, but ideally, it's easier if everybody's in the same section. But we're understanding because you can't possibly know that completely yet. Okay, and then one last starting point. I do think that understanding the hardware is valuable in just not only, like I said, what you buy and what you can do, but I think having a detailed understanding of the algorithms that are running this hardware and the hardware underneath it will change the way you write your code. And there's kind of a dream, which I share the dream, that like when our machine learning tools are good enough, then you can just get crappy hardware, and the machine learning will paper over all the details for you and everything will work beautifully. Maybe we're approaching that, but we're not there yet. And I think the labs that are doing the most impressive things on real robots with AI and autonomy have often spent a lot of time mastering what's happening at the low-level control stack. And they're not sending current commands to the motor. They're actually have a deep understanding of the low-level control that's running at high frequencies and stuff like that. Okay, so this is good stuff to know, even if you only care about higher-level ideas. Okay, we've had robot arms for a very long time. They used to look a little bit more like this. They used to be, and they still do. I mean, there's still lots of places where you'll see robot arms like this in factories or the like, and they're often behind cages or in rooms by themselves doing lots of incredibly useful work. But the robots have been changing over the last few years, decade maybe, and we're working towards this vision of cobots, right? Where robots that are working much closer to people, alongside people. This was kind of a, carefully chosen glamour shot for Rod Brooks back at the time when they were doing Rethink Robotics, and the point was that you shouldn't have to be afraid of having the robot drape its arms over you, right? Which was quite a statement at the time, right? And there's some important differences on sort of, the applications on the left and the hardware that was generated by those applications, and the applications on the right, which Rod, by the way, started that company saying, mom and pop own a bakery, and they want to be able to just unpack a robot and do some very simple things, and anybody can program a robot very simply, and it's going to be working alongside people. That was the vision for these kind of robots. And increasingly, the field has visions of getting robots in every home, right? And whereas the applications on the left, you want robots that are strong enough to lift a car and move extremely fast and are extremely precise, right? And that's different than robots that you're going to let hug you, right? And so the actual hardware underneath these things have changed, and maybe we're working towards this sort of vision of Baymax where you really, you want to cuddle with the robot. We'll see. Okay, but if you go into like a research lab today in industry or in academia that's working on manipulation, then there's kind of a standard cast of characters that you'll see in terms of robots. You'll see like universal robots. There's little ones and there's big ones, and they have different payloads and the like. You can see Rod's Rethink. The company isn't making the robot anymore, but they're still around. You see this Canova Jaco is a great arm that was originally marketed for being on the end of a wheelchair. So it's one of its incredible selling points is that it doesn't have a control cabinet you have to carry around. It's actually got all its electronics embedded in the bottom of the arm. So it's more mobile than most of them. And then the EWA you see, Panda is a newer version sort of the EWA in some sense. The people that worked on the EWA were involved in starting the company Frank Amica that made Panda and makes Panda. ABB is a more traditional robotic arm manufacturer. They build some of the big robots that you see in the factories, but they've also started making Cobots, these robots that are a little bit more huggable. That's too much. But okay, so before I go there. So there's a couple things that distinguish these sort of newer robots from the big ones, like I said. So precision versus huggability. But what makes it something more huggable, right? So if you take one of the big traditional robots, and if it bumps into something it didn't expect, it actually won't even have sensors typically that would detect these kind of failures, right? So a lot of times the only sensors that a industrial robotic arm will have will be just joint position sensors. So you're sending joint commands to the robot or trajectories to the robot. It's trying to execute them with very high precision. And if it deviates at all from that desired trajectory, it will fault. It'll say something went horribly wrong. I don't want to hurt anybody. I'm going to turn off, right? System error, and you have to reboot. And that makes them completely impractical for like use in the home, because you're going to bump into stuff in the home. Even if you have sort of, the reason I put this dishwasher example in again, so just take the example of the robot opening the dishwasher, which I showed you before. In the home, you probably don't know exactly where the dishwasher is. You probably don't know exactly where the robot is relative to the dishwasher. You probably don't know exactly where the hinge joint is. So if you want to do this sort of opening, which is moving along a constrained motion defined by the hinge of the dishwasher door, if you have any calibration error, uncertainty error in that, and you're trying to find a very rigid trajectory, the robot will simply fault. You probably can't do this task in a robust sense with a robot that's trying to do exquisite position control. It's just the wrong robot for the job. It was built for different requirements. Okay, so what's happened is we've seen a progression of those original robots towards things that can sense a little bit more of the world. So one of the first things you'll see is in one of the universal robots, for instance, you'll see force torque sensors at the wrist. That's a standard thing. You can take a traditional robot arm, put an extra sensor between the arm and the hand that'll measure contact force or at that joint or torques. And then you can write your controllers to be a little bit more informed about, I made a contact with the world somewhere in a way I didn't expect, and react to that. But that's a pretty common setup. There's a few arms out there that say that's not enough, that I actually need to be able to sense contact anywhere along my arm in some sense. And the way to do that is to add more instrumentation to the joints so that you could potentially measure a contact force or torque, an unexpected torque, even at the joints all the way up, because the wrist is only going to get it if you make a contact at the hand. If you bump your elbow into something, that's not going to be detected by the wrist force torque sensor. Okay, so the original arms, I'll start writing down some few words, keywords here. So original arms had joint position and or velocity sensors. And then you could start adding on force torque sensors, often at the wrist. Quick check, someone in the back, is that large enough, or should I write bigger? Okay, I guess I see thumbs up, that's good. I'll still try to write bigger because I got some feedback saying I should write bigger, but thank you for the confirmation, good. And then, and some of the, if you want even more than that, then you could try to do joint torque sensors. Right? And conceptually, what that's going to allow you to do is if I bump into something with my upper arm, then I have a chance of detecting that there was an unexpected torque or wrench at the joints. Even more than that, you'll see like the Baymax view is maybe to have, that's the big Disney inflatable robot. Maybe we'll eventually have tactile skin, and there's a lot of groups working hard on that. And there are fundamental limits to what you can do with joint torque sensing only. And at some point, you actually, if you want to be able to understand more about the contact you're making, you actually do need to have something more like a skin. Yes? So there's lots of different ways the question is, what does a tactile skin consist of? There's lots of different ways people do it. Sometimes people will just have arrays of loads of single axis force sensors, for instance, or even binary sensors. Sometimes they'll have an entire camera under the skin, and you'll try to actually sort of measure deflection of a soft membrane. That would be the other extreme. People call them visual tactile sensors. If we get to it towards the end, we could have a boutique lecture on tactile sensing and get into some of the details of that. Let me go behind you first. Yeah. Good. So the question is, what would you use? I used as an example that the torque sensor would be if you bumped into something. But if I wanted to pick something up and estimate its weight, for instance, that would be another application. Or if I was already in contact, maybe you could imagine an example of Tommy carrying one side of a table and the robot carrying the other side of the table, and we're working together. Then the contact forces that we're exchanging that I would want to measure through some interface like that could be very important. Yes? Yeah, so he asked about texture sensing. So certainly in the hand, people are investing in these visuotactile sensors, and some of them are amazing that you can actually see the prints. People, when they measure things with their sensors, they don't have cameras, and I don't have a camera in my finger, but I do have a different set of sensors that measure vibrations, and we can talk about those when we get to different mechano-vibratory sensors in the finger. Okay, so I would say most robots that just by quantity, like the number of robots that have been built, are more like this joint position sensor only, primarily. And then we see a lot of joint force torque sensors, and we're getting now, EWA is one of the examples of a system that went a little extra way to provide torque sensing at the joints. And we'll talk about how to do that. Yes? That's an extremely good question. So, right, so if I measure a force or torque, especially a point force or torque, then that's not enough to decide if I'm, it could be a person that's trying to command me, I should push this way, or it could be a wall that is immobile, and I don't have enough information just from that. So you need some greater situational awareness of the world in order to decide what to do with it. I think a very standard thing to do with it is if you sense torque you didn't expect, you stop, just so you have a safety case. You don't hurt somebody. But doing something better once you've made unexpected contact is a dream. And there's also, I think, another point to your question is having just a point sensor is often not enough to know. If you just have a few joint torque sensors, there's information limits of what you can tell. If someone was pushing you in two places, you might not be able to distinguish that between being pushed in one place or being pushed by a surface versus a point. There's kind of an information bottleneck there. Yeah. For sure. Yeah, that'll affect the way joint torque sensors are also used in control. Repeat the question. Good. Okay, so because these are so common, and this is less common, as we talk about control, you'll see that most robots today, most robot arms, let's say, are position controlled. Okay, as opposed to torque controlled. And that's a big difference in the way that we interact with the robot. It's actually fairly subtle why that is. And I think it's worth just saying it once for you. This is like, if you want to impress your friends at a party and you're talking about joint-controlled robots, this will be good for that moment. Why are most robots position controlled? It's a subtle thing. Like a lot of people know that they're mostly position controlled, but not many people know why. And here's why it's a little subtle, right? Is because most robots use electric motors. Okay, electric motors, we know that the current we put in to an electric motor is approximately proportional to the torque that comes out. And the voltage we put in is proportional to the speed we get out. Okay, so current in is related to, I'll say proportional to, it's not it's obviously more complicated than this in general, but is related to torque. And voltage is related to speed. So if I know how to do torque or current control, I know a little bit about electronics, we can do current control, that's not so hard. Why can't I do torque control? Just a second. Yeah. And yet, yeah. Yes. Okay. So even the electronics could be a bottleneck there. It's true, and in fact, people actually send PWM kind of commands down to the motor for efficiency type reasons and robustness reasons. Yeah, that's true. But even there's a mechanics reason too. Yeah. No, I think I could say I could send current commands possibly. I think that's not my reason. Yeah. Okay, that's a great point. So, torque is talking about accelerations and motion. So in both cases, whether we choose to send, command speed or torque or position, we're going to need some sort of feedback loop on the outside in order to accomplish, like you say, both motions, rapid motions, and sort of standing still. So in either case, we'll need a feedback loop. And you're right, I hadn't addressed that part of it yet. Let me tell you my reason. These are all good reasons, right? So the problem is that electric motors like to move fast. Robots, I mean, I like fast robots, but this is like thousands of RPMs potentially. I don't want EWA to move at thousands of RPMs, okay? Electric motors tend to produce small torque. They're most efficient in the high speed, low torque regime. And that's not what we want here. We want high torque, low speed, okay? So these things are high speed, low torque. And I want my robot to be lower speed, higher torque. So almost always, there's a big transmission between the electric motor and the world. And those transmissions are complicated and lossy and messy, and they break, right? So you can do that with pulleys, you can do that with more complicated things, but if you were to look inside here, and we will look inside here in a minute, you're going to see complicated transmissions, right, with harmonic drives or planetary drives, okay, that have gears meshing and lots of messy stuff happening in the middle. And the conventional wisdom is because of the friction and compliance. I mean, so gears do things, like when you put them under load, right? So the best case is you just have two gears and they're moving along and everybody's happy, okay? But already, if you just change your mind and move the other direction, there's always a little gap, okay? That's called backlash. So you get a little bit of a backlash when you go. That's the first thing. When you put them under load, the teeth of your gears are actually going to flex and bend, right? And then there's all kinds of friction happening inside here. So the conventional wisdom is that even though you can control the torque on the motor, that does not map nicely to the torque on the other side of the transmission. So if you want to control the torque at the joints, you can't just do that from the current. Okay, so how do you get around that messy transmission? You put a sensor on the other side, on the robot side, the output shaft, okay, and you try to close a feedback loop. So instead of commanding the motor side current or velocity, you'll try to command the robot side position or velocity or torque. And it's just much easier to put a position sensor on the output shaft of the robot, okay? And so you get big transmissions, current is no longer proportional to torque, to robot torque. Okay, so the solution to that is robot joint side sensing. Typically position sensors. Okay, and then we start at our first level of feedback control. We'll close a loop that sends currents to the motor in order to drive the output shaft to the desired position, velocity, whatever. Okay, and the most common form of that is a position controller that you'll see on a lot of robots would be a PID control, proportional integral derivative control. How many people have seen PID control? You don't have to have seen it, yeah? Good, yeah. So it's a good chance for me to just introduce my notation real quick here. So we're going to use Q for the joint angles. Okay. In general, Q will be a vector of all the joint angles, but in the single motor case, we'll just have Q be a scalar for one joint angle. I'll say Q desired is my desired joint angle. And then I'll use dot notation for derivatives. This would be the joint velocity. It's the time derivative of Q. Right? Yes? That's your choice, but typically it's internal coordinates, like a relative coordinates. Yep. Yep. So a solution here would be to command the torque of the motor, even if you don't know the details of the transmission, a pretty simple feedback control loop that does something like, this would be a gain, Q desired minus Q. This would be a proportional gain. Which says if the desired is higher than this is typically a positive number, it's always a positive number, I guess. When this is higher than this, then I want to just add more current, more torque at my motor. On the motor side, I can control that, right? That's the simplest one. So if I'm trying to be here, I'm actually here, push harder, okay? You would typically augment this with the integral and the derivative terms, okay? So you put an integral in here from 0 to t, dt of Q desired minus Q, okay? That's saying that, so the reason you need to do that, for instance, is let's say I'm trying to get here, okay? And I'm actually here. Gravity is applying a torque against me. So even if I just had a proportional control, then it will come to a steady state wherever the command I'm sending exactly balances gravity, but it's not actually going to have zero error. Okay, so to compensate for the DC term, the constant terms that you weren't modeling, you put in an integral term that will zero that out. Okay? And then you can do a little, I forgot my Ki. Okay, that's the integral gain. And then you would typically put a derivative term on here too. That allows you to track things at higher speeds a little better. Yes? So the question is, do you change these gains while the robot's moving? And the surprising answer is no, almost never. But there's actually a very subtle reason for that. And I was going to say that. So it turns out that PID control works shockingly well for robots, okay? And it's deployed often. And you typically just pick KP, KI, and KD once in the factory and you let it go. And that's surprising to me. When I really stopped and thought about that, I was like, wait a second. How does that even work, right? Because you would think if I'm holding like a jug of milk at full extension, then I'd be at a very different dynamic regime than if I'm having my arm down, right? the loads that the robot experiences are very configuration dependent. Even if I'm just holding my arm out, forget about the jug of milk, just holding my arm out is requiring very different torques than what I'm doing here. Right? Actually, some robots will overheat. If you take too long with your planning algorithm, with your robot like this, you might see smoke coming out. This robot and a lot of the more expensive robots actually put brakes in every joint. So when you're not moving, it'll actually turn the brakes on just so it doesn't heat up its motors. Okay. But what's surprising is even though the dynamic effects are very different, you can often get away with KP and KI and KD being fixed. So what's the alternative? So a lot of times people, in other fields, you'll see things like gain scheduled control, where you'd have in different operating modes, you might use different gains. Like in an aircraft doing interesting things, you'd expect to see a gain scheduled controller. Okay, so it's actually pretty subtle why that works. And the answer may be a problem for some of you on your homework, but I'll give you a quick view of it here. Is this sort of important thing called reflected inertia. So if you think about, I guess you've all played with pulleys over your life, right? The Museum of Science, you have the little kid pulled down the enormous weight because of a pulley, right? And I guess we've got a type of pulley even in this animation there. Pulleys are trading speed for torque. Okay, so what's happening, and we're doing the same thing in this joint. Right? So we have a motor moving at high speeds now in order for the output to be moving small, and a little bit of torque here acts like a lot of torque on the other side. Right? But that goes both ways. Okay? That goes both ways. And it turns out that the relationship, if you think about it, if you work it through, which it's worked through in the notes, is actually that the reflected inertia of the motor, okay, so the motor has a little bit of magnets in it. Typically electric motors will be made with magnets like this, okay? And those magnets are moving around. So there's some inertia. This is reminding you all of your physics backgrounds, right? There's some inertia inside the motor, and it's moving around. But it's moving around wicked fast, okay? And it's being scaled by the transmission. So actually, the inertia of the motor that is felt on the robot side is actually multiplied, the rotor inertia times the squared of the gear ratio. Okay? And similarly, if you're looking from the view of the motor on the other side of the transmission, the robot has inertia, okay? But that inertia is actually shrunk by the squared of the gear ratio in the other direction when you get to the motor. So the motor, shockingly, even though these are typically tiny motors and big heavy robots moving things around, the motor has to do as much work or more work sometimes just to move itself around at high speeds that it has to move the robot around at high speeds or low speeds. That effect, when you multiply, so the gear ratios in these transmissions on this robot, for instance, is 160 to 1. 160 squared is a big number. And you take your inertia of your motor, even though that's a small number to start with, it is comparable to the inertias of the robot. Okay? In fact, I think we worked it out at one point for the EWA, it's like, 85% of the inertia of a link comes from, don't quote me on that number, but it's a surprisingly big number, that comes from moving the motor around instead of moving the robot around. That's a counterintuitive maybe effect of having a big transmission. And what that means is when the motor's doing all its work, it's sort of irrelevant where the arm is, right? Or if it's holding something or not holding something. You'll feel it a bit, but you feel it just as much just moving those motors around. And it has an effect of making it so that you can, when you're designing tuning in your controllers, you don't have to worry too much about the configuration of the robot. Did I say that clearly enough? I could say it in equations, but I think that's the main point. Question about that? Yeah. Yeah, so independent is a little too strong. You can still heat up your motors. I did say that, but the motor inertia is unaffected by the weight, or the rotor inertia is unaffected by the weight, and the weight that you're carrying gets scaled by the transmission squared on the motor side. Thank you for asking that. Yeah. Okay, so there's actually been a movement, an effort over the years to try to not do that. Yeah, please. Yeah, so that's a great question. Would you want to implement the gains, control gains in electronics, for instance, or in mechanics, or but analog electronics would often be a great way to implement this. Although computers are so fast these days that the sample frequency of a digital implementation of that, which can be a little bit more configurable, they're running at 10 kilohertz on a robot and it's fine. The inertial time constants are low relative to the 10 kilohertz. That's like well over your mechanical frequency. So I'd say most people have switched to digital and said that's good. But definitely when we were slower, it was like, let's think about doing analog versions of it. That's a great question. So there's a movement, there was a movement that was popularized at MIT many years ago, actually, this was recognizing the equations of motion of my arm, where the arm actually gets affected by the gear ratio squared. So those are roughly the equations I would have written if I'd written it all out, okay. And they said, well, what about not using, what would it look like if we built robots that didn't have big transmissions? Let's say, we'll call a direct drive robot one that's like gear ratio 10 or less, let's say, maybe 20 or something. Okay, depends who's selling. And we'll call those direct drive robots. And it was interesting, back in the day, the direct drive robots had these ginormous motors. It was like, little arm with a big motor attached, and that was good. But now you'll see them, they're more common. We've gotten better with our motors. We've got outrunner motors are kind of a cool thing. It started with quad rotors and airplanes and stuff. And now they're more popular in robots. So like Songbei's Cheetah Lab, for instance, does things close to direct drive now on a lot of his Cheetah robots. And that's a more viable alternative than it used to be. If you can get rid of the transmission, then you can think about doing torque sensing or torque control by looking at the current on the motor side. Okay, which is powerful. But there's a reason we use gears. I mean, the motors are happy at high speeds, right? So, okay, yes.
So do torque sensing robots also have position sensing?
For sure. The torque sensing robots also have position sensing. Yes. Position sensors are like commodity, so almost every robot has it. Okay, so let's just take a second to look at our family of robot arms. So this notebook is there for you. This is our EWA, and you can play with it. All the joint angles, slide them around and see what happens. Whoops, I could print it, but I don't want to do that. Okay, but like I said, you can also do things like look at the inertial properties of the robot. So here's the inertia ellipses of that robot. This is just of the actual links of the robot. Okay, so what is an inertial visualization of the robot? Like what does that mean? I mean, so this robot in particular is very curvy and complicated. It's hard to like do inertial computations in your head, okay? So a standard thing to do would be to take each link of your robot and replace it with a canonical ellipse that is the same size as if you had the density of water, okay? And it's the same position and orientation, all right? So if you were to replace and just say the robot is the density of water and it's made up of these equivalent geometries, from a dynamics perspective, that's an equivalent representation of the dynamics of this robot. But it's easier to think about and visualize, okay? And sometimes, actually I know for a fact, I could do this. If you get different robot descriptions from the manufacturer or whatever, right? This is just a different version of the EWA. I'm pretty sure. I didn't actually check this, but yeah. So it's actually also a really good debugging tool. So let me see if I can do this, okay? So we noticed this the other day. So the description format you get of the robot from the manufacturer actually just has bugs in it, and the inertial ellipses of the even links are rotated by 90 degrees. Okay, great. So everybody's been working really hard on their controllers, and your inertia estimate was just wrong. But that's why you visualize things, right? So I'm embarrassed that we didn't notice that. Actually, we knew about it probably 2 years ago. I thought we had fixed it everywhere, but we found this one model of the robot that's still not fixed. It'll be fixed soon. Okay, that's super valuable. But just to say that reflected inertia one more time, I wish I had made the visualization now, but if I were to look through the lens of the motor and try to make sort of an equivalent visualization, it's like there's a little circle at every joint of the robot that's getting blown up by the square root of the gear ratio to the point where the picture would look something, if I had just like a one-link robot, and I had an inertial ellipse of the link that sort of looks like this. There's a little motor here, which accounts for relatively little of the mass of the robot. But its effect on the dynamics looks like a big inertial ellipse that's centered exactly at the joint. So when you're moving this joint around, the effect of the link is actually small, can be small if the gear ratio is large compared to that. Yeah? No, it's not included in the visualization. I wish I had. That's a homework for me. And then you can see, you download the manufacturer's specs for all the, whoops, that's just a space. You can play with all the different robots, and that one's zero position is in collision, which is awesome. That's why you have green arrows of contact forces, because it's hitting itself. But I do think you can basically, for your projects, for instance, you can just pick your favorite robot, and for the most part, it'll work. This one is also in collision at 0. Awesome. Here's the UR3. Okay, but they're all there. Right, and we have, the robotics world has an ecosystem now where the manufacturer will publish their specs, and then we fix them a little bit, I guess. But then, yeah, you can work with any robot.
In that, a lot of motors are sort of flat and like down. Is that sort of how about?
Yeah, so I think there's different types of motors. So some of I think like some you see frameless motors and stuff like this that can be very big and flat. It would depend on exactly which technology you're looking at. Yeah. Yeah. So Songbay's got a particular way of winding the coils to get closer to direct drive, and they tend to be much wider. I'm not an expert in his latest designs though. Yes.
You mentioned there's a type of robot which has wheels for the containers.
Yes. So I'm biased, but I think Drake's awesome. And the mechanics engine is awesome. And one of the best tests we had, my daughter was doing FTC, First Robotics, and she had a Mecanum wheel. And we just put in the geometries of the Mecanum wheels, rollers, and that thing just drove just right. It's not tire mechanics, right? But it's just the friction of the contact forces of the ground or whatever. You could drive it around. It was super fun. Maybe I'll put that as an example. So you can simulate that. It's not simulating tire mechanics. So typically if people are doing like racing cars, they will have special purpose, magic tire models and the like to capture the pneumatic tires on the road and stuff like that. We're not doing that. But in terms of a basic physics engine of rigid bodies interacting and getting the right forces, it'll do all of that. This one doesn't have wheels. We'll have versions that have wheels coming up. Okay, so yeah, if you want to do torque sensing, then there's various ways to do that. Let me show you how EWA does it. The basic idea, of course, is that you put somewhere in your linkage, but on the robot side. So the motor's over here. Got a lot of different This is a harmonic drive gear unit. And on the end here is a torque sensor that's measuring the joint torque. It's a beautiful, I think torque sensing, to get it right and performant requires exquisite engineering. And I think they've done an incredibly good job of this. Strain gauges are finicky and the like, but there's some incredibly good engineering that makes torque sensing viable in this robot. And it's a little extra shaft at the end of the robot. Okay, and that allows you to do things like stop if you run into something and you didn't expect, or potentially do better control. And one of the ways that was popularized, actually, when this is Sami Hadaden, when he was a student probably at DLR in the German Aerospace Research Lab, and he's showing off how valuable it is to have joint torque sensing in order to make safe human-robot interaction. But it's just sort of, I love that as a sort of famous set of videos because he just keeps hitting himself at high speeds with a robot to make a case. And Sammy's like a pretty established roboticist now. He was one of the founders of the Franka Emika company later, but back in the day, he was hitting himself in the head with robots at high speeds, right? And making the point that that having the ability to sense a force and a control system that can stop quickly enough. I mean, that still looks like it hurt. I don't know, but they built up. His thesis was about building safety cases for robots, right? And it really can be a difference maker. It also allows you to do different types of control. So I told you that a lot of our arms will actually fault if you deviate from a commanded position. Okay, but if you're thinking about more in the torque space, then you can say maybe my goal is just to be able to produce some amount of torque at the end effector. When I'm in contact, I'm going to push with a certain amount of force, and I don't care what position I'm in, right? Or I'm going to, even more interesting maybe is if I'm going to produce a certain stiffness at the end effector. So I want to say that I'm going to go to some normal position, but if I push, I want to act like there's a spring between me and the target position, okay, and produce forces to let that go. So this is an example. We'll talk a lot more about it later, but when we'll do an actual one lecture later on the low-level control. But the first thing they do to show they've got mastery of the dynamics of the robot and torque control is they'll show, first of all, that they can just cancel gravity out and make the robot act like it's not there. That's the standard gravity comp video that you'll see. That's how you earn bragging rights, saying I've got a great torque controller and great torque sensing, as you show you do gravity control. And then, I guess I didn't include it, or did I include it here? Next. Nope. You can also do, we'll see impedance control and some of these other things that work naturally once you have joint torque sensing. Yeah. Yeah, that's really good. So, typically we're going to bring your own hand, or bring your own barbell. It's kind of a weird hand to bring, but or you might pick up some objects. The interface for this, which is what commands the low-level software, allows you to specify an inertia of the load of the end effector. You'll typically, even a dexterous hand is not a constant inertia, but you'll just kind of pick a canonical pose of it, compute the inertia, and tell the robot low-level controller about that, so that when it's doing gravity comp, it's pretending the hand is always like this and just a statue. And then you treat the fact that it's doing this as noise, as a disturbance. Yes? That is true. Yes. So PID control is not doing gravity compensation. You can do them both. You could do gravity compensation first, and then, so if you were to take this controller and then just add on plus tau gravity comp, for instance, then if your control system is capable of doing this, if you're doing it on the joint torque commands instead of motor commands, then that becomes viable, and you can still write things that look like a PID control, but also cancel out gravity in a feed-forward term. And we'll talk about that in some detail later. Yes, please.
The resolution of
Yeah, so at the end effector, you can on this robot, it's a few newtons of force you can detect, and depends on the robot, but they're not exquisitely accurate. You know, if I hit it with a feather or something, maybe I wouldn't notice it. Sorry, if I was pushing down on a table, it's newtons, yeah, and then so that is related through the kinematics to some Newton meter resolution. Yeah. Okay, there's a few other ways. So that's one way to accomplish joint torque sensing, and that's the way that this robot did it, and the Panda does it. The Jayco, I think, does not do it that way. But there's another way that is you might hear about, which is good to know, that's called series elastic actuators. It's actually the same way, but it's emphasizes something different. So series elastic actuators, which says I'm going to take my motor and I'm going to put a spring in series with my motor, and then this is my output shaft, okay? And you could think, actually, I mean, of course, the EWA has a strain gauge on a sheet that is actually, you could think of as a very stiff spring, where the reason the strain gauge can measure anything is because that piece is deflecting and it's measuring the forces. But whereas the EWA sensor, torque sensor, is, I think, I estimated at one time to be something like a stiffness of 5,000 Newton meters per radian. A series elastic actuator, like maybe the one you'd see in Baxter, for instance. I'm going to go back. Yeah. This robot was also capable of torque sensing, but a series elastic actuator, SEA, will typically be much lower. And they don't always publish their specs, but I was guessing that this one was around 100 Newton meters per radian. Okay, so this is kind of a different philosophy in actuator design. That robot can be stiff and follow position trajectories well if you want to, but you can also measure the torques. This one, I don't want to say it can't be, but it can't be very accurate in some sense. It's got, between the motors and the world is a pretty soft spring. So you go and push it and it feels squishy, right? So this is a very different regime. And a spring is a torque sensor because you can measure the deflection of the spring and estimate the force or the torque, okay? So this time, now if I just take my old conventional sensors, which work really well, and I measure the position of the output shaft and the position of the motor shaft, and I estimate that difference, then I've got the deflection of the spring, and I've got a good torque sensor. I want to distribute the questions, yeah. Yeah.
Is it possible to control
So the question is, can you produce one or the other from the other one using control? And the answer is yes, up to your bandwidth limitations. So there is actually some bandwidth limitations of your motor. Your motor can only change its command at a certain frequency, for instance. And there is a mechanical bandwidth that comes from the spring. So you will at some point have a bandwidth limitation on your whole system that will be lower bandwidth capable on the very soft spring. So I think the best motors might not be able to act like a stiff spring if you've got an SEA. And I think in practice we see that difference. You can also do, Baxter was a famous series elastic actuator, a Heavy Robotics. There's a few others that market these series elastic actuators. You can also do torque control with hydraulics. If you choose to build a hydraulic robot, this is the Atlas robot. This was the first version of the Atlas robot. That was a hydraulic robot. So if you're pushing fluids around and you have valves, then the differential pressure across the valve is proportional to the forces or torques that you're producing. So that's another option, but less common. And even Boston Dynamics, when they went to build Spot, made an electric version. I think that's extremely good for laboratory and development and stuff, but it's a little bit less viable maybe to have those in the world. Okay, that was kind of a quick run through robot arm hardware. Any other high-level questions? Yeah. Yeah. You read both sides of the spring, and that's actually, so by virtue of reading the output shaft, you do know where you are in the output shaft. It's the difference of those two signals that tells you the deflection of the spring. So you always do have that output shaft. It's just a matter of whether you can control it, right? Your PD control might not be able to regulate a position command accurately. Good question. Yes? You can do linear or rotational joints for almost anything I've said today. You can, so I've seen both. Sometimes I've seen electric motors with ball joint, with screw joints that are, the spring is actually a linear spring. I've seen rotary springs. Yeah, either one is possible. Cool, okay. So let's go from the robot arm hardware into a simulation, okay? And there's more to it than just the physics, right? So we talked about the hardware station diagram abstraction, and EWA doesn't take in torque commands. It takes in position commands, and then an optional feed-forward torque. That's the messages that the control box that you get when you purchase the EWA is listening for. And it outputs the commanded position, the measured position, the velocity, estimated, the state estimated, the torque you commanded, the torque measured, all these different things, the torque external. Okay, so it's trying to say, these are the torques that I expected from my robot mass and the barbell that I told it about, and then from the difference. And you can just look at the torque external and just see the unexpected forces. Okay, but how do we actually achieve that in let's say our simulator here? I'll stop this old one. Okay, so the first thing to know is we have a physics engine. That physics engine is called multi-body plant. Plant is then, comes from the world of controls. It was originally chemical plants, but it's stuck. And now anything we try to control, we tend to call it a plant. At least I still do. The younger people don't. But okay, multi-body plant is our physics engine. And if you look at the multi-body plant diagram, okay, then this takes torque commands as input. This would be like the torque at the joint, for instance. We don't normally put the motor dynamics in. We could put it in there, okay? But this is a torque command input, and it takes and computes the updated body angles, joint angles, positions, velocities, accelerations, and things like that. That's the core physics engine. Okay, so the second thing you need to put your simulator together is, we call it it's our geometry engine here, which is for rendering and contact and stuff like this. Our geometry engine is called scene graph. This is a common name. You see a scene graph in any sort of computer game world, okay? This is collecting information about the mesh files that you used to define your robot. It can answer queries like how far away are these two meshes from each other, which are some pretty heavy computational geometry happening inside the scene graph, but it can also very quickly tell you if things are in collision or not, okay? And that's almost enough to put together a simulation. But you need a few more little pieces. So you have to populate the physics engine from disk, from some description of the robot. This is the one we were looking at before. So you parse an EWA model from a description format into the multi-body plan. So I'm going to add the model from file, and then I'm going to make sure it's not, if I left out this weld frames command, then the robot would fall down through the world. Yeah, what's up? Nope, they're separate systems, and they're wired together. Yeah, okay. And the robot description format, you typically don't have to write them yourself, but you might want to check them. They're just these standard sort of text description formats, which says I have a link here, it's at a certain position, it's got a certain inertial matrix, it's got a mesh file that shows me how to render it. It has certain material properties. Okay, so if you did find a robot, if you're making your own robot and you wanted to add it to the simulator, you would end up writing a robot description file like this. But nowadays, you mostly just find the existing ones and use them. Okay, and then scene graph is this simple thing that takes in poses and outputs all the geometry information. And if you put that together, I'm going to run all the way down to this one. And you run your little simulation. And this is what happens. Okay? I commanded 0 on the input port, and I just ran my simulation, and that's what EWA does. Okay? The torque command is 0. That's, so I've never seen a real EWA do that. If I did, I would quickly assume that the robot was broken. So don't do that, right? But that is a complete physics description of the EWA, right? And the rendering enough to make the geometry work. Yes?
For like actual the force that is like by default, is that something that the manufacturer includes?
That's exactly the point. So the point is that I don't send 0 torque to this. The robot, the control cabinet is doing some extra work to do gravity compensation, to turn the brakes on and off. Okay. Right now, since it's not plugged in, the brakes are just locked and it's sitting there. Okay. But in general, I have to, in order to understand how my commands are going to affect the robot, I actually need a mathematical model of that low-level controller. Okay. So that's the next piece. There's various ways that we can model that. I think we know what the governing equations are, but partly because they run it at 10 kilohertz on specialized hardware, and we don't want to slow down our simulator to run it that way. We actually make slightly different models, abstractions of that controller on the real robot. Okay, so we can add our an inverse dynamics controller as a simplest model of what's happening on the robot. It's one more diagram here, one more element in the diagram here. It takes in the estimated state, the desired state, and produces torques. Okay, and if I add that in, then I get a diagram. Oops, what did I do? Here we go. I get a diagram that has the plant, it has the scene graph, it has the state of the EWA that's coming out from the plant, pumped into the controller as the estimated state. I've set the desired state to 0, okay, and then I just put the force back through. That's my whole new diagram. And now I get sort of the expected result of it just sits there, which is more boring, but more correct, right? Okay. So the point is that if you want to build up a simulator, you actually have to model the low-level control. And you have to model it well if you're going to do higher performance things, because that will impact. There's even the way that it interpolates, like you send position commands in sequence, it will extract an effective velocity command using some approximation. And if you don't model that correctly, you're not going to be able to do very high bandwidth kind of controls. That's the state interpolator business. Okay, and then the whole thing comes together to be this, gives you this abstraction of having positions in optionally additional feed-forward torques in and the states out. That's just a bigger diagram. Yes? So I should be more careful. We do have support for rotor inertia and reflected inertia, but we don't model the lower sort of, so we only model the motor at that level of detail. So we just assume it's a lumped mass or lumped inertia that's reflected through with the reflected inertia. However, a lot of simulations don't include that because the reason I know that, and not only because I've looked at the other simulators, but also because the robot description formats that everybody uses doesn't even have a field for reflected inertia. You know, which is like, they just missed that one, and it accounts for, you know, some huge percentage of the dynamics of the robot. So I think a lot of people worry about how accurate the simulators can be for manipulation, but they forgot a big one on that one, so. Cool, okay, so that's a basic story of, you know, robot arms. I wanna spend the last few minutes talking about hands, yeah? So bring your own hand. I did bring a bunch of my own hands. I also, like I said, slightly broke them on the drive over here, on the walk over here. But let me just tell you a little bit about hands. So everybody who does robots, I think, is somehow fascinated by dexterous hands. Okay, you can't, you know, you can't not like the idea of having a human-like hand on the end of a robot, right? And there are some famous ones out there. This is the shadow hand. The Allegro hand is here. It's another sort of famous one. And the shadow hand was made famous by the OpenAI experiments of trying to learn Rubik's Cubes, for instance. But these are very delicate devices. I think they hammered on this like crazy, and they had to improve the robustness of that like crazy in order to do the experiments you saw in the reinforcement learning papers there. And I think in general, most people would say that dexterous hands are still not quite ready for mainstream. They're very much a research product. If you go down the dexterous hand route, you're gonna expect lower quality sensing information, things that lose calibration, things that break, cables that snap, stuff like that. But that's, I mean, that's good for research. That's good, that's where we wanna be, right? But the argument, the counter argument, the few people in robotics that don't love dexterous hands or whatever, I think have a pretty reasonable argument, which is that maybe you don't need a dexterous hand to be useful in the home, right? And the plainest argument I like for this is just to say, if I were to give you one of these little grippers and ask you to go into the home, you could still be pretty useful, right? You can do a lot of stuff with a big brain and a simple claw, right? And the people that made that argument the best, I think, is when they built this PR2 robot. This was many years ago now, okay? This is a tele-operated robot, so there's a human looking through the camera and of the robot and driving the robot around, and this is sped up a little bit. But basically everything you'd want a robot to do in the home could be done with that kind of interface and a simple two-fingered gripper, okay? I mean, we've seen lots of examples of places where it sure would have been nice to have a few more fingers. We see it in our own research where it just takes you longer to do things if you have to, like, if you want to pick up a mug and set it down in the dishwasher, okay, and it's in the wrong orientation, and you got your two fingers, you got to set it back down, pick it up like this. You can do it, it's just annoying, whereas a human would just do in-hand reorientation and then set it down, okay? So, but you can do a lot of things with a big brain and a simple hand. So because of that, we're actually going to do a lot of work in the class with, to start off, like in the simpler case, with a two-fingered gripper. This is the force-controlled planar gripper from Schunk. It's called the WSG. It's kind of the EWA of grippers. You know, you have force-controlled, torque sensing kind of things. And this one is more bring your own finger, right? So you can actually put various different end effectors on it. I've got a version here that has some visual tactile sensors mounted on it. You can just change out the fingers, but I also have the simpler fingers here that you can play with. Okay, there's a lot of, it's a big back drivable robot. I just got the power light to turn on, that's cool. And we'll spend a lot of time on this. I saw you, did you have a question? That's true. It becomes a packing problem of like how much can you fit in a small space, and where do you run the wires, where do you run the cables. So people have, I think I'll show you a few of the clever ways that get people to get in between them. But it's still an open problem, I think, for design and for control of those things. So here's the ones I brought today. I've got a Sandia hand here, which is a beautiful, fairly dexterous hand. Okay, it's got cameras in its grippers, in the gripper there, which is, I actually expected those to be more useful than they were. It's kind of, like you can only do so much when so you can sort of see what you're gonna do, but then when you get close, it's just like, so we ended up using those more. We were using those on Atlas. We would occasionally go like this and put one hand out so we could look at what we were doing over here, because this one was kind of, just didn't help that much. You'll see a lot of people will mount cameras on the wrist now, so you get a little bit of throw. Actually, Spot also has a camera in its palm. This is the iHigh hand, the iRobot Harvard Yale hand. It's a beautiful sort of under-actuated hand. I'll tell you more about that as we go. Okay, of these robots that have less actuators than degrees of freedom in the hand, and cables and springs to make them still useful. The Robotic three-fingered gripper, this is the one we use the most on Atlas because it's extremely robust. We actually, this is a beautiful, beautiful hand, and the story I'm about to tell you is completely our fault, not iRobot's fault. But we were working with Atlas in the competition, and we had to pick up these boards, like 2x4s, and throw them out of the way. It was a disaster response. So it's like there's boards strewn in front of the door. You have to get through, so you have to pick them up. And we went like this. We picked up the board, and we had snapped a cable in the hand. So now for the rest of the competition, we had to walk around holding a 2x4. We were like trying to do everything with our left hand, and they're like, "Why are you holding the 2x4?" Well, our hand broke with it completely welded on the thing. So after that experience, we went to these like massively rigid, strong hands. It's a beautiful but heavy hand. We actually fell on top of it. We dropped the robot. Our walking controller failed and landed on top of it. And it was bent, but we bent it back and it kept working. So that's the other end of the robustness trade-off. And then the Allegro hand I mentioned before. This is kind of, there's newer versions. You'll see a few research labs. Poolkits Lab has been playing with one here. There's a number of groups that have been trying to make a newer version of the Allegro hand using Dynamixels, if you know what those are. So I think it's a good time to be thinking about hands again. There's also like a ridiculous number of humanoid startups all of a sudden. So this is Sanctuary AI, and they're all trying to solve the problem of making humanoid robots, and they're also trying to like simultaneously solve the dexterous hand problem, which is awesome. That's great. So hopefully, I'm sort of optimistic that the world will have more robust dexterous hands soon. Let's just see what comes out, right? But it's not the only way to do it. There's also like this world of people making very clever mechanisms to solve manipulation with hands. And one of my favorite here is, you can see, robot grippers based on granular jamming media, okay? The story is very simple, okay? You take a sack, you fill it with coffee grounds. And this is your manipulator, okay? You put a vacuum behind it. You just let your coffee grounds sack, sink over whatever you're gonna pick up. You suck the air out of the inside. The coffee beans jam, and it becomes rigid, and it picks up anything. Like, watch this. This is just incredible. Okay, it's literally coffee grounds in a sack. That's the actuator. Yes. Right, so all they did was suck the air out, and the coffee grounds jammed themselves together. Okay, super simple, super durable. I guess you could probably slice it. And it could pick up anything, right? It's not so good for like buttoning your shirt or tying your shoes, but for just picking stuff up, it's pretty darn good, I think, okay? It's a real egg, yeah. Okay, so that's a pretty good one. There's also a world of people building soft hands now. Okay, so things that are using soft actuators potentially, certainly soft materials to make, these are pneumatically actuated hands. They have valves that are expanding and contracting in order to make the fingers move, and they can be surprisingly interesting devices. And this was of course a play on the OpenAI example of trying to make a in-hand reorientation, okay? But that was with a simpler hand. This is the grippers that I've got here. That's actually a combination of trying to make a soft hand, but also integrating tactile sensing. So it has some of the benefits of having the hands, but it also has a depth camera behind the bubble and some dots so that you can estimate shear and other things inside there. Very simple design, but I think very well done. And it's impressive what you can do with it in terms of force sensing and geometry sensing in the hand. Like, unlike the hand that's sort of looking at this, if you leave a little gap, then you get to actually see the deflection of the skin and do interesting things. There's a bunch of mobile manipulators. We'll talk. I'm gonna allocate a little bit of lecture time definitely to talk about mobile manipulators. Carefully thought to be right before you finalize your project ideas, so that maybe a bunch of you will do mobile robot kind of manipulation for your projects. Okay, this is the PR2 I showed you fun examples of. Fetch and HSR were kind of one-arm versions of it. This is the Everyday Robotics project from Google. Spot, of course, you know. So I think this is okay. Mobile manipulators are obviously good, obviously interesting for research. It's extremely hard to buy one. There's not really many that you can buy anymore. The PR2 sort of eventually died, and you really can't buy as fully featured as a PR2 manipulator today. So there are not as many around as I'd like. And so Spot, in some ways, is one of the better choices for mobile manipulation. It's kind of frustrating just in the sense that you can't see the table. You gotta only use the hand camera to sort of see the table that you're trying to manipulate. It'd be nice if it had a head, but it's pretty good. Of course, TRI actually built their own custom hardware, and I think groups that are working on seriously on mobile manipulation are often in the position of building custom hardware because we don't have great mobile manipulation options right now. I think as soon as it becomes commercially viable, then we'll see lots of great hardware coming out. But we're in a sort of a quirky time right now where they're not available. Okay, so I want to end by telling you about my favorite robot of all time. Okay, it's kind of, it's the thing they ask you at parties, like write on your name tag, what's your favorite robot of all time? And I answered that I like this high-speed hand by Ishikawa. Okay, so the idea here was we're going to build a semi-dexterous hand, electric motors, but we're going to just forget about the fact that motors overheat. We're going to overclock our motors, basically, remove all of the safeties, and just inject a significant amount of current for a small amount of time into these motors and see what we can do. And this is actually a long time ago, okay? But they got some wicked fast and it's super awesome. They did it also for tracking cameras. This was before computer vision worked. You had to track, white objects on gray backgrounds. But if they did it with a foveating camera and high-speed actuators, they could do that. They had actually some tactile sensing. But you're going to love what this thing can do. Okay, dribbling. That's like easy to write on there. Pen spinning, okay? Rowing, that one's pretty cool too. Okay, this is high-speed video. Here we go. I'm not sure what the choice of the middle finger was doing, but this is like way more dynamic than you see on the average hand, right? Pen spinning, pretty good, right? pretty good. Okay, I'm going to fast forward to the end here. This is my favorite. Regrasping, okay? This is a cell phone, right? I have to believe that only worked once, but still, that is awesome, right? Okay, one of the best robots of all time, for sure. Okay, good. We'll move on to more of the control next time. If anybody wants to come and see the hands, you're welcome to come down and look.